Hi everyone. Welcome to the first episode of Rackside Chat with industry expert by ASA Computers and Racklive. In today's episode, we will dive into how cloud native processors are transforming AI computing. I am Ruban Kanapathippillai from ASA Racklive. ASA Racklive is focused on providing innovative solution and superior technology expertise at competitive cost and enterprises. Actually, for example, I am right now sitting inside a data center which we own in the Silicon Valley. This is where we do our integration and testing. We are one of the only integrators who does integration and testing in the Silicon Valley. Today, we joined by Tony Rigoni from Ampere Computing. Welcome, Tony.
Welcome, Ruben. Thank you so much for having me here today. It's a pleasure to talk with you.
So Tony is head of AI business development at Ampere Computing. Can you give us a little background about yourself?
Sure, love to give you. So I've been with Ampere now a couple of years. My background is mainly around a lot in what I'll say anything from edge devices, sensing, automation, a lot of automation, self-driving vehicles, a lot of computer vision, and all basically, if you want to say, a lot of predecessors and stuff of AI today. The last year or two, we've moved more Gen AI, some of the large language models coming out. So very much familiar with those. And the whole idea is what we're trying to do is how do we promote this and how do we make it sustainable for AI and for users to use it?
That's great, Tony. So if you look at it, I mean, I've been thinking about the AI ML evolution over the last 10 years. And if you think about it, it was simple AI and ML and at the devices and, little bit level people were using. But suddenly, last 3 years with Chat GPT and generative AI, it has gone mainstream significantly. What do you think? Where do you guys see as a AI working out on your life as well as from a generative AI evolution point of view?
It's definitely come on. I mean, you brought up a good point. AI has kind of been around for a long time. And if you look at traditional AI stuff like machine learning, computer vision, recommender engines, those kinds of workloads, they've been around. They've been running on CPUs and everything in the last several years. Over the last couple of years, you said the large language models come on, Chat GPT and stuff. That's required another level of horsepower of processing. So that's why you've seen the big influx of GPUs into the market now to do some of that processing. But with all this said, this is around, there's a lot to do, and we'll talk about it a little later, but a little training versus inference. And we really do want to talk about the differences between the two and what's going to happen, because the market right now has been primarily on how do we train all these models? How do we make them working? Where we're moving to now is more of basically how do we deploy these models? So really the runtime, if you want to think of it that way. And that is where we talk about inference and how do we inference at scale and how do we do it low cost enough and power effectively enough that we can put this at mass and help, really democratize AI inference.
Yeah, I mean, let's dive into some of these area. Before that, I recall using ARM architecture in late 1990s in communication application and management processes. Those were developed for low power and 32-bit architecture for communication application at that time. I remember using that one in various market when I designed my first controller chip for telco. I was using that. But how did Ampere identify the opportunity to leverage the transition from low-power communication 32-bit architecture to a 64-bit server architecture with a high-performance environment? How did you guys get into that business?
It's really part of our founder, Renee James. Years ago, she recognized, I'll call it the coming power crisis that we're having. And if you look at traditional architecture, x86 kind of base architecture, it is to get more performance, you have to put more power into it. And at the time, though, if you go back, 10 years, even 5 years ago, power was readily available. It was everywhere. It wasn't that expensive. Power companies were giving out to data centers very low cost power and everything like that. So it wasn't a big issue at all. So who cared about power? We just put more power to get more performance. What we've seen, as everyone knows, in the last, especially few years, there's been lots of changes. Especially regionally around the world too. You have crises going on in Europe there where power, literally double the cost of power. Here, living in California and stuff like that, there's been the proliferation of like EV cars, electric cars, which are sucking power from the grid now and everything. So power costs have gone very much high and skyrocketed. So this is now becoming very hard for power centers and for data centers to basically, number one, it's gotten very expensive to run stuff, but number two, they are capped at how much power they can get. So the only way to solve this is really to move to more of what I'll call a power efficient architecture. And this is what the ARM architecture delivers. And as everyone knows, and people don't know, ARM architecture is basically, like you said, all mobile devices. If you think of, every cell phone out there is basically powered by an ARM processor. There's more ARM processors out there than any other kind of architecture. It was designed from ground up to be for like battery power. So very, very power efficient, opposed to the x86, which was more power inefficient, just an older architecture. Our thought there is, well, let's take this great technology and let's scale this up a little bit. And by adding more cores and all that, now we get the performance that we need to, but at that low power savings that we.
No, I think you hit it right there, because rather than using x86 where it came from, because they had very complex instruction set, with the RISC, simpler architecture, they are built from the bottom up for the lower power. So if you look at it, AI and generative AI, which has been in news lately a lot, even if you don't like it, AI has to be there. And as you earlier mentioned, the training and inference applications are identified as the main use cases for that. Ampere's cloud-native processor has been positioned as cost-effective and energy-efficient alternative to legacy x86 processors for AI inference application. Can you explain how these processors are tailored to meet the specific demands of AI inference compared to traditional solutions?
There's a couple key things there that make our processors doing running AI very well aboard our processors themselves. One of the few things, and just more of a technical detail nuance that goes out there, is compared to x86, people know the performance from doing things like multi-threading or hyper-threading. And basically what it's doing is taking one core, and when it needs to throttle up, it's stealing power from the next core to throttle up. So we kind of call it the noisy neighbor problem. It works fine for like a desktop or for certain applications where you have unused cores and you can use that extra power from them to get more performance. When we look at AI workloads, though, they basically run the same basically almost full throttle on all the cores at the same time. There's no way to pull power from a neighboring core to do that. So what we see is x86 companies, they're telling even vendors to basically shut off multi-threading or hyper-threading to get the best AI performance. We recognize this from day one, and our cores are basically single-threaded. So every core is the exact same, and every core gives the exact same performance no matter what. So by doing this, we eliminate any kind of jitter from going core to core, and we have much more consistent capability and much more, I'll say, consistent performance. That's the best way to say it. The second thing we've done is we've actually we've optimized our silicon. We've written software to optimize it for the common frameworks out there. So things like PyTorch, Onyx, TensorFlow, the new Llama CPP, that framework people are using. We've optimized these frameworks to run on top of our architecture. So this helps us by using our optimized frameworks, stuff like that. We're seeing almost 2x or 3x performance increase on AI inference workloads. So it's a combination of architecturally, we did good, plus software that allows us to do very well at AI inference.
No, that's very, very nicely put, because you guys thought about holistically, but then you started from the foundation at the simple RISC core with ARM architecture that was able to control and achieve the low power part of it. Another interesting thing, which as an integrator, as sell a lot of into a lot of data center, we are finding out the biggest problem is not the servers, not the system, but finding energy. Because if you have to build a data center somewhere, you need to have a lot of energy, a lot of power, important part of it. As AI rabbit's growth has led to exponential increase in power consumption, as highlighted by the energy requirement and large models like ChatGPT. How does Ampere address these challenges, And what role does energy efficiency play in the design of your latest processes?
Yeah, like we mentioned earlier, the coming energy crisis, and now we're starting to see it today. All these servers now going in there, especially for AI, all these workloads, you're talking servers are running, not just hundreds of watts, but thousands of watts. And so you're getting racks are literally like a couple servers per rack. The rest of the rack
Yeah.
is empty, and you can use it for a coat hanger if you'd like to. But realistically, the key to here is what we done and what we said is there's two kind of ways to look at this. One is we talk about right size computing a little bit later, but you use energy efficient. So if you're running a lower AI model, so if you're running a Llama 7B or 8B, and you're doing just a couple users, it makes sense to run it just natively on CPU. And in that case, our CPUs are very power efficient, like we said, much lower power than anything out there, high performance, and run great there. What we see in a lot of data centers, though, they say, well, we do need an accelerator for larger models or things like that. This is where we really come into architecture. What we don't talk a lot, we should talk more about, is traditional servers today. They have a server with multiple accelerator cards or GPUs in them. Almost every single one, to get the PCI lanes necessary, they run a 2P configuration. So 2 CPUs per server. Because we have 120 PCI lanes built in there, we could run off a single CPU. So we could run the same amount of GPUs using a single CPU versus our competitors running 2 CPUs. So that right there is basically 1/2 the amount of CPUs, a more power efficient CPU, which draws the power level down at the rack or at server level. What we've seen is, I know it's only a couple hundred watts that we're saving each server, but you take those couple hundred watts and you push it over a rack level, it means you could fit in 1 or 2 more servers per rack, increasing your density, increasing your compute per rack at the rack level. So you're getting more performance using the same amount of power as you would before. The other thing we like to talk about too is there's a big trend now. People don't realize also, there's the power of the server, but for every watt you use running a server, it requires another watt to cool it. So people don't talk about that very much, but there's a double benefit to, for every watt I could cut out of the system, I'm actually saving 2 watts.
Yeah.
The key to this is, that one big thing about this, by having this low power, we can still run air cooled. There's a big pushing towards liquid cooling, which adds complexity, adds cost, adds a lot of things. So we do believe the future is still staying air cooled, maximize performance with air coolness. And the only way to achieve that is by resonant low power.
Correct. Because one of the things which we are at Racklive ASA lately investigating a lot of liquid cooling. How do you cool all these processes, GPUs, and the system and the rack level and all that? And by providing a solution which can extend with beyond with the air cool, that reduces the cost, that reduces the infrastructure investment, reduce the challenges. Like for example, if you have liquid cooling, there are positives, but there are negative in the sense, how do you manage, how do you do replacement and all of those. The second part of it, which I am working on also, is a AI appliance we are trying to launch at ASA Racklive, where we would be using Ampere ARM-based solution, because we don't need to do a lot of GPU capability or accelerator capability, because you have 192 cores or beyond that, and it is interesting to see from that point of view. We need to make sure, like, people are buying these high-end H100, H200, and various GPUs, as well as very high-performance x86 servers. But the problem is they are not using all the resources all the time. So the concept of right sizing AI compute to avoid over provisioning is gaining traction. How does Ampere approach help organizations optimize their AI workload, and what advantage do cloud native processors offer in that context?
Great question there. We truly believe right size compute is what everyone needs to look at. And to your point, it started with a trend of everyone bought, H100s, for example, do all their training on, and then it's kind of like, well, we have the systems here, let's use them for inference and all that. And really, that's many cases an overkill for what customers are looking. So you're running a Ferrari and you're trying to just get to work, So what we like to say is we like to say right size computer. And how I look at it is, and I view the world as almost like t-shirt sizes: small, medium, large. And for us, small is basically running inference. Like I said earlier, small models, maybe less users or something like that. Latency, maybe it's something that aren't latency important, but you could run those directly on CPU. We've proven out before, like on one of our CPUs, we could run roughly 120 tokens per second, which is very good performance. So that's a t-shirt size small, I'd say that. And right there, you're gonna have lowest power, lowest cost. It's the most cost value way, if you want to think of that to do AI inference. The second medium would be basically an Ampere CPU, because our power use is less than x86, married with an accelerator. So it might be one accelerator, two accelerator cards married together. And this allows us to run like what I'll call class 2 models, which fall into that, things like Llama 70B, if you think of that kind of size category. And that's t-shirt size medium. Large then is when you're running multiple GPUs, accelerators, to run larger angles or large, heavier workloads or more users. And that's where, once again, by having lower CPU power, you stack it up the rack level, and you're going to get extra server to increase your performance density. So it really doesn't matter if you're at small, medium, or large. We can help out each side of the right sizing. But we tell customers, use what's right for your application. Don't just buy t-shirt size large and run small applications on it.
Yeah, thanks. I think that you explained it well. So I'm going to ask a little bit different question from an application point of view. From a large language models and all of these are important. But if somebody is watching our video and see about our end market, end use cases point of view, because you have been expertise in automotive and various aspects of it, can you elaborate on what are the markets you guys are going after from the AI compute point of view?
So AI compute, from what we're seeing today is, we're still in, I'll call, the early phases of AI, almost the Wild West. We're trying to see where it's actually going to reside. We're seeing markets, several different markets using AI today, whether from computer vision, so stuff like automotive, smart cities, manufacturing. Lots of use cases in vision, retail, think of smart stores and stuff like that. Used a lot in those kind of applications. In the large language models, we're seeing that open up to many different use cases. Stuff like what we're seeing is stuff like legal contract. Let's do all legal summarization. Let's do that. Stuff paralegals used to spend hours doing. We're seeing a lot in healthcare. Drug discovery. Patient outcome identification. A lot in finance industry. Looking at trends and models and stuff. Of course, chatbots are everywhere and popping up more and more. But to sum it up there, basically, I
see all of these because as we
work, they're everywhere. It's everywhere. What's really fun? So the key is you have the flexibility to really move it to wherever you need to be. So we've kind of talked about, and you brought up a concept, and we're going to talk about AI compute.
Yeah.
Where we see AI compute is it's if you look at traditionally most data centers today, they have a rack of GPUs and they have a rack of traditional AI traditional like x86 or so servers running. Today, the GPUs are doing the training mostly and sometimes running inference. The CPUs are running everything else. So think about your databases, your Nginx, your Redis, all these kind of other workloads it's running. That's how it's done today. It's disjointed, two different things. When we talk about AI compute, we see AI becoming, like we mentioned these use cases earlier, AI is going to become part of every single business or business service or a business application. So it's just become embedded in it. It's not going to stand alone. You're not going to just go run this AI application. You're going to have AI running in your CRM program. You're going to have AI running in your, when you call centers. It's going to be part of a larger workload. As such, AI needs to live near where the data lives. Usually databases and stuff like that. Where we see the future is going to be is much more customers. Number one, AI is changing every day, so they need the flexibility of the future. But more importantly, they need to scale for demands. And what we see is more the servers of the future will be basically a combination. Every server will have compute capabilities running from large core processors, like our 192 core processors, mixed with several accelerators. And if you look at it at the rack level, you start thinking about this way, is a third of that rack, roughly, just throw out a number here, a third of that rack is going to be doing fixed AI all the time. It's going to be running on those accelerator cards all the time. A third of that rack is going to be doing fixed traditional compute workloads all the time. Database, memory, web services, all that kind of stuff. We look at it as that middle third, basically, is extra CPU cores that you're not using that you can now use to either run AI workloads, smaller AI work, or run additional compute workloads. So it gives you that flexibility to kind of meet whatever the demands are. But the whole point is the whole world will be basically running off the same kind of racks and servers, and it'll all be integrated into the same package. It won't be disjunction like it is today. And so that's the term. Yeah, we use AI compute for that. So.
Yeah, I think you covered all the use cases. So as ASA computers, we are in the process of building an appliances for addressing some of these area where enterprise AI, where they can take it inside and run their own model and own documents, and they extract information out of that. So it is very much aligns with what Ampere can provide from their compute and their framework point of view. As AI continue to evolve, how does Ampere see its innovation prepare organization to meet future AI compute and maybe energy demands in the future? How do you see that evolves?
The only way, the proper way for CPUs to meet the energy demands and meet the future needs, you cannot scale up. When I say scale up, I mean faster frequencies, which was traditionally what we did. More power, more frequencies. You can't scale up, doesn't work. You have to scale out. And scale out means more power efficient cores. Like we said earlier, we started, Ampere started originally shipping 80 core processors, then 128. Now we're shipping 192 core processors. Our next gen on our roadmap, we're already looking at 256 core processors on a single processor. And we've even talked out there on a roadmap, the Ampere Aurora project, which will be about 512 cores, along with a specialized compute interfaced with it. All this we're looking at will be air-cooled. No liquid cooling, low power enough so we can run it air-cooled. The extra cores, like we talked about AI compute, is there for the flexibility. And that's why you need for the future. So because the average server life now, it's 3 to 5 years that you're going to stick that server in there before you're going to pull it back out. You need enough cores you stick in there. Yes, maybe you don't need the 192 cores today. Maybe you're only using 80 cores. But software could change tomorrow. Demand could increase. Now we have the extra cores we can just use as needed. When we're not using them, we can start powering them down, idling them to lower the power usage of the servers. You're not running full throttle all the time. So there's a lot of energy savings to be had there too, which reduces cost.
No, that's an excellent way of finishing our session, because if you look at it, how old the large big x86 architecture was evolved versus where you are coming from, where you can control in a micro levels and then utilize, and all these, not just that, if you look at from ChatGPT, OpenAI, and all the big guys, they are doing this huge language model training. But if you look at it, where the AI is going to be democratized is by enterprises using so many of their own data, training on own information, and doing that. For that, where Ampere sitting is, in my opinion, is going to be very optimal and going to drive a lot of growth from a volume growth point of view, rather than trying to do from a high performance, high power control part of it.
Yeah, I'd like to just double click on that 1 second, because what you said is a perfect point, and I know you guys are working with us to try to get this out there. The challenge we see today, like we said, you mentioned we're in a training phase, we're moving to inference. The challenge we see today is it's still very expensive. Inference, AI, as a whole, everything is very expensive. How do we lower the cost so enterprises could run this? You brought up another good point, which is about the future AI. And I said before, AI will leave near the data source. The chat GPTs and all that, it's an open public source. Most companies' data they actually run AI on is locked up behind walls. It's not in the public cloud.
Yeah.
So they're going to want, enterprises going to want to deploy AI locally, on-prem in the private data centers, private clouds. It is going to be running near the data source. And this is what we're really focusing on. How do we, number one, lower that cost to run it, so it becomes low cost, so that they can actually be profitable and get the fruits of the actual AI out there. But totally in alignment with you guys, and I'm really
we are so excited to work with you guys, and thank you very much.
Thank you very much. Thank you, Ruben, very much. It's a pleasure to be here today.
Bye.